Hi, my name is Gabe. I'm a mathematician and a tutor, and I'm excited to work with you all on some statistics today. Today's topic is calculating confidence intervals for single population means. We will start by briefly reviewing the structure of confidence intervals. We will then specify the structure of confidence intervals for application to a single population mean. Finally, we will take a look at how this process works in practice, particularly regarding the student's t-distribution. We will get started by reviewing the general concept of confidence intervals. As we do this, let's think about social networks. People are connected to each other in any number of ways, but it might be nice to know a basic property, perhaps the number of friends that an average person will have. As a population parameter, we will call this number mu. Because of the complexity of friendship networks, we can never calculate a population parameter exactly, so we will have to rely on a sample statistic, which we will label as x bar to represent that it is a mean. In general, mu and x bar are used to represent population and sample means respectively. We will provide numbers for this example later on in the lesson. So, rather than pretend that the sample stat is equal to the population parameter, we are going to construct a confidence interval which will give us an interval estimate across which we expect the population parameter to lie. The purpose of a confidence interval is to provide a bounded estimate of a population parameter based on a calculated sample statistic. With this in mind, let's recall the general structure of a confidence interval. Confidence intervals all begin with a sample statistic at their center. From there, we add and subtract by a factor consisting of two components: a multiplier, which is dependent on the desired confidence level and the underlying distribution of the sample, and a standard error. The standard error is a function of the sample statistic, some metric of the sample variance, which we'll discuss for each statistic, and the sample size. The following table summarizes the components of this general structure. The sample size, sample statistic, confidence level, and standard error are all required to calculate a confidence interval. Notationally, the confidence level is frequently associated with the value 1 minus alpha, which is itself the significance level. This is important when consulting lookup tables for multipliers. For example, a 95% confidence interval requires a 5% significance level. For the single population mean, we will focus on the sample size, the sample mean x bar, a confidence level, a multiplier related to the t-distribution, and a standard error, which will rely on a standard deviation calculated from the sample data. Let's start by actually writing down some equations for this confidence interval. The confidence interval for the mean value of some population parameter is equal to the sample mean plus or minus a multiplicative factor. This factor includes the t-multiplier, which we write down as t star, and a standard error term. The t-multiplier is a function of the significance level over 2 to specify that we are working with a two-tailed confidence interval, and the sample size, or more specifically, the degrees of freedom in the problem. For the single population mean, these degrees of freedom are simply equal to the sample size minus 1. In general, this multiplier is bigger for higher confidence levels and smaller when there are many degrees of freedom. The standard error for this problem is equal to the standard deviation of the sample data divided by the square root of the sample size. This term tends to get smaller as the sample size gets bigger, or when the data is more tightly packed around the sample mean. When we put this together, we are able to make a claim about the probability of a population mean being found within a certain range. Explicitly, we can write that the probability that mu lies between x bar minus t star times the standard error and x bar plus t star times the standard error is equal to the confidence level as a probability. Written down, this is an intimidating formula, but just breaking down each term should allow us to work with it relatively easily. Let's see how this works with our example, particularly regarding the calculation of t star. As you recall, we were working with a question of the number of friends that the average person in a network has. Let's provide some numbers on a sample that we have collected from this dataset. After sampling 50 people, we have a sample size of n equals 50 and a corresponding 49 degrees of freedom. After calculating the average and the standard deviation of the number of friends reported by each person, we have that x bar is equal to 19.8 and the standard deviation s is equal to 2. From this data, let's construct a 95% confidence interval for the population average, which gives us a confidence level C of 0.95. To do this, we're going to need to calculate a value for t star and for the standard error. Given that we have a confidence level of 95%, we are going to need a t star at a 5% significance level divided by 2 corresponding to the two-tailed confidence interval. Let's take a further look into the t-statistic first. The most important aspect of the student's t-distribution is that its shape varies with the degrees of freedom of the dataset. In particular, the distribution is wider and flatter for smaller datasets and degrees of freedom, and narrower when the dataset is larger. The black line represents a t-distribution for 5 degrees of freedom, while the purple line represents the distribution that we need for our problem with 49 degrees of freedom. Lookup tables or calculators for the t-distribution will always ask you to input the degrees of freedom, so make sure that you keep track of this during your calculations. For our purposes, we need the t-statistic for a 95% confidence level or a two-tailed 5% significance level with 49 degrees of freedom. Let's consult the following t-table to find this value. T-tables have 2 critical components. Moving vertically will provide values for different degrees of freedom, while moving horizontally will correspond to different confidence levels or significance levels. Recall that we are looking for a confidence level of 95%, which corresponds to a two-tailed significance level of 0.05 at 49 degrees of freedom. Zeroing in on the 95% confidence level column and the 40 and 60 degree of freedom rows, we see that our t-value will be somewhere between 2.021 and 2.000. Since 49 is about halfway between 40 and 60, we can approximate our t-multiplier as 2.01. As a rule of thumb, the t-statistic for a 95% confidence interval will generally be very close to 2. To calculate our standard error, we recall that the standard error is equal to the standard deviation of the sample data divided by the square root of the sample size. Since the standard deviation is equal to 2 and the sample size is 50, we can calculate that our standard area is 2 over the square root of 50, or approximately 0.28. With all this information, we can finally start to construct our confidence interval. The confidence interval can be calculated as the sample mean plus or minus the t-statistic times the standard error. We know that our x-bar is equal to 19.8, our t-statistic is equal to 2.01, and the standard error was just calculated at 0.28. Take a moment to see if you can work out the value of the confidence interval on your own. Hopefully you were able to take a minute to look at that. The lower bound of the confidence interval is equal to 19.8 minus 2.01 times 0.28, which is 19.2. While the upper bound is equal to 19.8 plus 2.01 times 0.28, giving us 20.4. Now let's put this in terms of probabilities. Specifically, we interpret these results as meaning that the probability that the true population parameter mu lies between 19.2 and 20.4 is 95%. Hopefully, this example has helped you to see how to calculate the confidence interval for a single population mean. In this lesson, we demonstrated that the confidence interval for a single population mean is calculated from the sample mean, the sample standard deviation, and the sample size combined with information from the student's t-distribution. We started this lesson by reviewing the general structure of confidence intervals. We then showed the formulae for single population mean confidence intervals, particularly the form of the standard error. And finally, we explored the student's t-distribution and the impact of the sample degrees of freedom on its shape. We then calculated an entire confidence interval using the information from a sample problem. This video provides an example of how to go about calculating a confidence interval for a specific sample statistic. Other sample statistics will require slightly different formulae, but the basic procedure will remain the same.